Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 4, Integrals. Section 4.9 and 5.4, Antiderivatives and the Indefinite Integral.
Lesson 4, Integral Formulas.
So our next topic that we're going to look at is just writing down a bunch of integral formulas. And usually we do, in a sense, memorize these formulas, but they are all formulas that come from familiar derivative formulas. So it turns out that now that you've memorized the derivative of a lot of functions, it's not so hard to then go ahead and figure out what the integral is. And I tend to kind of think backwards in my head each time. I think, okay, I know this particular derivative formula. I think backwards and figure out what the corresponding integral formula is. So it just depends on how much you like to memorize things. I always like to memorize as little as I possibly can and derive everything else. So the idea is that if we're given a derivative formula, it automatically gives us a new integral formula. And that's because of this relationship between integration and differentiation. Integrals are really the antiderivatives of a function. So there's that close relationship between them. Let me give you an example. Suppose I have the derivative of tangent x. That is equal to secant squared x. That's something that we memorized back in the previous chapter. Well, that means that I have an integral formula. It means that if I go backwards, if I integrate secant squared x dx, what should I get as an answer? Well, when I'm integrating this, I'm thinking, what do I have to differentiate to get this as an answer? And here it is. Tangent x is the thing I have to differentiate to get secant squared x as an answer. So the integral of secant squared x is tangent x, and I think I even made you think out this one by thinking backwards earlier. But just to show you that every time you're given a derivative formula, automatically you have some new integral formula by essentially just writing it backwards. The integral of this answer will equal whatever we were originally differentiating. Well, the same thing is true for a lot of other things. Actually, let's look at this example down here because this is one that I had you do earlier. If I want to know what's the integral of 1 over x dx, we can kind of think of the derivative formula backwards. We're really asking, what do I have to differentiate in order to end up with 1 over x? So to get the answer to this integral problem, we're thinking backwards. And what do I have to differentiate to get 1 over x? Well, we talked about this earlier in this section. We said that you differentiate the natural log of absolute value of x and you end up with 1 over x. So the answer to this problem would be the natural log of absolute value of x. But of course I could add on any constant. If I were to differentiate that constant, it would just give me 0. So this derivative formula gives us this new integral formula. Let's go ahead and think about these others. For example, integral of e to the x dx. Again, you can probably just think backwards. We know that the derivative of e to the x is e to the x. It's its own derivative, and that gives us an integral formula. And what would our integral formula be? We're saying, what would I need here to differentiate to get e to the x? And according to this formula, I would need e to the x. It's the function I differentiate to get e to the x. And then just remember to add your plus c onto the end. This one with the integral of a to the x is slightly more complicated. So let's see if we can think about that one. You might keep in mind the derivative formula for a to the x. It's almost like the derivative formula for e to the x. Remember, derivative of e to the x is e to the x. This is almost equal to itself. It's almost equal to a to the x. But do you remember what extra factor we had to put in front? We, I think, used the chain rule in order to prove this. but we did this in an earlier video. The derivative of a to the x, where a is any real number constant, is a is any positive real number constant, is ln of a times a to the x. And remember that since a is a constant, ln of a is a constant. So kind of keep that in the back of your mind. We'll use that fact. So it's just this number. If a is 3, for example, and we're differentiating 3 to the x, the answer is ln of 3, which is some decimal number. It would actually have an infinite decimal expansion, times 3 to the x. So that was a formula that we had from differentiating. So if you're trying to think, well, what's the integral of a to the x, you might make an initial guess and say, well, its derivative is almost itself, so maybe its integral is itself. Maybe the integral is a to the x plus c. I'm going to put a little question mark here, so this is really just a guess. This is just a guess at this point, and I don't really know, but how could I check that guess? If I were to check it, you notice that there's a little problem that comes up. When I check it, I'd go back and differentiate my answer. I'm guessing this is the right answer, but when I differentiate, I'm going to be taking the derivative of a to the x, and we just said that's not a to the x, it's ln of a times a to the x. And then, of course, the derivative of the constant is just 0, so that drops out. But I don't end up with what I want. What I wanted was to match what was originally asked, and I want to match this a to the x, and that's not what I have. I have ln of a times a to the x. It's a little bit like when we were developing the power rule. We have an extra annoying constant here. So this is an annoying constant factor that we don't want. We wanted to check it and end up with just a to the x here. We don't want ln of a times a to the x. We wanted just a to the x. So how do I get rid of that extra annoying constant? Well, we can do it very much the way that we did with the power rule. We can fix up our guess. So I'm going to put fix our guess, and I'm going to think, what extra factor could I put out in front of the a to the x? What fix-it factor could I put in front that would end up canceling out this ln of a when I differentiate? And the fix-it factor we can use is just the reciprocal of this constant. So what I'm going to put in front is a 1 over ln of a in front of my a to the x. And again, that's just some number. It's a constant. 1 over whatever ln of a, whatever number that is, times a to the x. So my claim is that the integral formula, the integral of a to the x dx, is not quite equal to a to the x, but it is equal to 1 over, let me write that in red, 1 over ln of a, that number times a to the x. So that's what I claim is the correct integral formula for the integral of a to the x dx. Notice it looks rather similar to the derivative formula. For the derivative formula, derivative of a to the x is this constant ln of a times a to the x. The integral formula is rather similar. It's 1 over that constant, 1 over ln of a times a to the x. So there is sort of a symmetry in the formulas there, but I haven't really checked this yet. I just claimed that that's the fix-it factor that works. Well, let's check it. So this check didn't work because our guess was wrong. Let's try this and see if this guess is correct by going back and differentiating. So I'm going to take the derivative of ln of a times a to the x. Remember that 1 over ln of a is a constant. So when I take the derivative, that constant multiple gets carried along. And my derivative will be the same as 1 over ln of a, whatever that constant is, times the derivative of a to the x. But the derivative of a to the x is this formula, ln of a times a to the x. Well, I should have put a plus c on here, I'm sorry. Okay. So what am I saying then? Let me write this a little bit neater over here, and I'll write it right under our formula for the derivative of a to the x. I'm saying that we now know how to integrate a to the x dx, or at least I think I know how. I think I fixed it up correctly. The derivative of a to the x is this constant ln of a times a to the x. It's almost its own derivative, but it has an extra factor of ln of whatever the base is, a. I'm claiming that the integral of a to the x is also almost equal to itself, a to the x, but that the constant that's out in front is 1 over ln of whatever my base is, 1 over ln of a. It's that constant multiple of ln of a. And of course, with an integral, I have to add on my set of all possible integration constants, c. So you notice these formulas look rather similar to each other. When we differentiate a to the x, we get ln of a times a to the x, and when we integrate a to the x, we get 1 over ln of a times a to the x dx. Well, I haven't really checked my answer here. I'm thinking that this is the right fix-it factor. To check it, all I would have to do is go ahead and take the derivative of what I'm claiming is the answer. So I'm taking the derivative of 1 over ln of a, that constant, times a to the x plus c. And remember that this constant multiple just gets carried along, 1 over ln of a times, and I find the derivative of a to the x. Well, the derivative of a to the x is this thing, ln of a times a to the x. So that's the derivative of this. And of course the derivative of c is just 0. And sure enough, the 1 over ln of a and the ln of a cancel out, and I end up with a to the x, the thing that I was asked originally to integrate. So it matches this a to the x. So now we have a formula for the integral of e to the x, for the integral of a to the x, it's this formula, and for the integral of 1 over x, which is related to the natural log function. So we've talked about different integral formulas that involve exponential and log functions. Okay, let's go ahead and look at a few more familiar derivative formulas and see how they help us to find integral formulas. So let's go ahead now and look at some integral formulas that involve trig functions. And I'm going to start with this one at the top, the integral of cosine x dx. So the question I'm asking in my mind is, what function do I need over on the right-hand side so that when I differentiate it, I'll end up with cosine x? And that function would have to be sine x. And of course I can add on any integral constant c. Is that correct? Well, we can always check by going back and differentiating. The derivative of sine x plus c, well, derivative of sine is definitely a positive cosine x, and derivative of c is just 0. So that definitely checks, and I get back to the function I was originally asked to integrate. Let's try the same thing with sine x. You might initially think, oh, integrating sine x, wouldn't I get a cosine x plus any constant c? Well, that's a good guess. Let's check it. I'm going to take the derivative of cosine x plus c. But unfortunately, when I take the derivative of cosine x, what do I get? I get a minus sine x. And then the derivative of c drops out. But I wanted to end up with a positive sine x. So what do I need to do to fix up my guess in order to make this work out correctly? Well, it's not too hard to fix up. I could put an extra minus sign in my guess. So now my guess is the integral of sine x equals minus cosine x plus c. So if I'm going to check that guess, I'm taking the derivative of minus cosine x plus c. And that means when I take the derivative of that, I have an extra minus sign that I am carrying along. So my answer over here when I take the derivative would be minus the derivative of cosine x. So that's minus a minus sine x. And that does come out to be a positive sine x. So that checks out. I want you to notice that I wrote these formulas in co-function pairs. Cosine and sine are a pair of co-functions. And you notice that their integral formulas, just like their derivative formulas, are very similar if you memorize them in co-function pairs. So the integral of cosine x is a positive sine x, and the integral of sine x is a negative cosine x. So I always remember these in co-function pairs. I usually remember the ones that are in the left-hand column, and it will turn out that the ones in the right-hand column are really the same formulas, but with the corresponding co-function inserted wherever there was a function over here, and they will all have negative signs on this side rather than positive signs. This one we already did. The integral of secant squared x dx we said is tangent x. So I won't check that one because we did that one earlier. And yeah, in my mind I could check it quickly. Derivative of tangent x is secant squared x. Okay. Here I have the co-function to the secant function, cosecant. And the integral of cosecant squared x turns out to be the same formula I have here, except that I will insert the co-function associated with tangent on this side. So instead of equaling tangent, it will equal its co-function, namely cotangent x plus c, and there will be an extra negative sign. Let me put that in green so it's easy to see. There's an extra negative sign in front. In other words, the integral of cosecant squared x is minus cotangent x plus c. And that's fairly easy to check. I'll let you check that just by going back and differentiating the right-hand side. The integral of secant x tangent x, okay, we haven't done that one, but let's try to think backwards. What function do I have to start with here so that when I take its derivative, I end up with secant x tangent x? And you may remember that the derivative of secant x is secant x tangent x. So if I were to check this one, derivative of secant x plus c, yeah, the derivative of secant x, remember, is secant x tangent x, and the derivative of c will just be 0, and so that one checks. And you can probably guess then what I have over here. Notice cosecant is the co-function of secant, and cotangent is the co-function of tangent. And so the formula that I get over here should look just like this formula, except that I'm going to substitute the corresponding co-function. So instead of secant here, I would want cosecant x plus c, and there will be an extra minus sign that comes into the formula. So it will actually be minus cosecant x plus c, and I'll leave it to you to check by going back and differentiating. So if you know these three formulas that are on the left-hand side, and you just remember to replace all of these with the corresponding co-function on the right-hand side and throw in that extra negative sign, you don't have to memorize quite as much. Okay, well, let's talk about inverse trig functions. And again, every derivative formula that we have will help us to get a new integral formula. This is a really weird looking function. I'm asked to integrate 1 over x squared plus 1 dx. I have no quotient rule for derivatives, so there's no way, for integrals, excuse me, so there's no way to integrate, say, the top and integrate the bottom of this separately and somehow divide the answers. That just won't work. However, this may look familiar to you. It's actually the answer to a certain derivative problem. So I'm asking the question, the derivative of what would equal 1 over x squared plus 1? So let's think back to our derivative formulas, and what do I have to start with? What do I have to take the derivative of to end up with an answer of 1 over x squared plus 1? Well, you might remember that that is an inverse trig function. It's the inverse tangent of x. And we did quite a bit of work to show way back when we were doing derivatives that the derivative of the inverse tangent function is 1 over x squared plus 1. So this derivative formula gives me a corresponding integral formula. The function I need here then is the inverse tangent of x, inverse tangent x, and then of course I can add on any c. So just as we said on the last page, this derivative formula automatically gives us a new integral formula. Well, we can do the same thing here. We're trying to think backwards again, and we're thinking what inverse trig function should go in here so that its derivative would end up being 1 over square root of 1 minus x squared. And the thing that I need to put in here, you have to remember your inverse trig functions, would be the inverse sine function. So the derivative of the inverse sine of x is 1 over root 1 minus x squared, and that means that this derivative formula gives us, I'll say so up here, this derivative formula gives us a new integral formula. The integral of this weird thing, 1 over root 1 minus x squared dx, is exactly the inverse sine of x plus any constant. Okay, how about this last one? This again is a really weird looking function, 1 over x root x squared minus 1. We're supposed to integrate that, but again, remember that that particular function is associated with the derivative of an inverse trig function. So you have to remember those formulas. The derivative of the inverse secant of x turns out to be 1 over x root x squared minus 1. That was one of our formulas from our derivative chapter, and that gives us a new formula for integrals. So the integral of all this stuff is the inverse secant x plus c. Now, it would be possible, let me just draw sort of a dotted line here, because these were just the derivative formulas that gave us those integral formulas. It would be possible, actually, to write down the integral formulas that correspond to the inverse trig functions, the inverse cotangent function, the inverse cosine function, and the inverse cosecant function, but we don't actually need them because they really just will give us answers that are the opposites of these functions, and so these are the only ones that we actually need that give us really useful new integral formulas. Okay, well, let's go ahead and try an example. So one example would be this one. I'm asked to do the integral of theta squared minus cosecant squared theta d theta. Well, this is two separate terms, so I get to integrate term by term, so why don't I break it up? It's the integral of theta squared d theta minus the integral of cosecant squared theta d theta. And this one, I could actually just use the power rule on. We're used to having an x here. This is a theta. That's okay. We're integrating with respect to theta. So I'll use the power rule on that. And so I'm going to have theta to the third power, and I need a 1 over 3 out in front. So I've integrated that term. Integrating term by term, I now concentrate on the integral of cosecant squared theta. And we have that right up here. Cosecant squared x. If I integrate that, I get minus cotangent x plus c. So if I had cosecant squared theta, and I'm integrating that with respect to theta, I would have minus cotangent theta. And then I add on my integration constant. So this one I could just go ahead and simplify. It would be 1/3 theta cubed, minus a minus becomes a plus, cotangent theta plus c. So we are actually able to integrate a lot of things, partly because we had all these derivative formulas, and they automatically give us these new integral formulas. Okay, let's go ahead and look at the next page. So on the next page, we have a whole bunch of things to try, and I'd like us to start with the example at the top, and I want you to try that one. So pause the video, give it a try, and if you get stuck, we'll go through it together. Okay, let's try this one together. Again, I have two terms, so I can break this up and integrate term by term. I can do the integral of e to the t dt and this other integral separately, and I'm noticing this is 10 over t squared plus 1. I could think of that as 10 times 1 over t squared plus 1. So I'm kind of recognizing that 1 over t squared plus 1 from the formulas on the previous page. So when I break it up into the integral of this thing plus this thing, I'm also going to pull that constant multiple of 10 outside the integral sign, and I would have a 1 over t squared plus 1 left inside. So just treating the 10 as a constant multiple allows me to get something that's looking a little bit more like a familiar form to me. All right, so integral of e to the t dt. E to the t is its own derivative and its own antiderivative. So the answer there would just be e to the t. And then I add on, and I do 10 times whatever the integral of 1 over t squared plus 1 is. But what did we say? If we look back at this page that we had, maybe I'll put that up here just for a moment, we said that was one of our special integrals. The integral of 1 over x squared plus 1 was the inverse tangent function, the inverse tangent of x plus c. So again, it doesn't matter whether these are x's or t's, doesn't matter what variable we use, as long as we're integrating with respect to the same variable that appears in this form. So this thing is the inverse tangent of t. Sometimes we'll put that in parentheses, so you can either write inverse tangent t or inverse tangent of t. And then just remember to add a single integration constant onto the end. Okay, well, why don't you try the next two? Pause the video and then we'll go through them together. And don't forget on this one that there is no quotient rule for integrals, so you're going to have to think about rewriting that before you take the integral of that expression. All right, well, let's try these together. I'm going to break this up into the integral of each term. For this one, when I do the integral of this part, 4 over root 1 minus x squared, the 4 is a constant multiple. I could pull that out, and I would be left with 1 over the square root of 1 minus x squared dx. And then this one's just minus the integral of sine x dx. Okay, good. So that at least breaks it down some, and now the 4 is a constant multiple that gets carried along, and I just do 4 times whatever the integral of 1 over root 1 minus x squared is. And what is that integral equal to? Well, that should be familiar as the derivative of something. That's what we talked about right here. Integral of 1 over root 1 minus x squared dx is the inverse sine of x plus any constant. So that again is one that we are familiar with. This is just the inverse sine x function. And I'm going to subtract off the integral of sine x. And remember to be careful about the signs here. The integral of sine x, we said, is actually a minus cosine x. That's because the derivative of cosine x is minus sine of x. So I end up getting minus a minus cosine x. And this would look like 4 inverse sine x minus and minus becomes a plus cosine x plus c. And again, to be absolutely sure, you can take these answers that we've gotten in this example and also in this example and go back and differentiate them. You can do it in your head if you want to, or write it out, but it's always a good idea to double check by going back and taking the derivative of whatever you think the answer is. Okay, how about this last one? Did you find a way to rewrite this? Because I can't just do the integral of the top and the integral of the bottom separately. There is no quotient rule for integrals. I do have a single term in the bottom, so we could do something similar to an example that we did a little bit earlier where we had a single term in the bottom. Then it's convenient to break this single fraction up into two fractions with a common denominator of w squared. I'll put parentheses around this. And usually we're taking fractions and adding them together into a single fraction. Here I'm splitting it apart into two fractions, each of which has the common denominator of w squared. The reason for that is that if it happens to be a single term in the bottom, I can then simplify each of these remaining fractions and write them as powers of w. This one would become w to the fourth over w squared would be w squared. This one, if I just wrote it as a power, I could do that. It would be 3w to the negative 1. But you may remember that that is the one power of a variable that our power rule does not work on. When we have a negative 1 here, if you try the power rule on it, it will not work. In fact, we could even try that and then we'll fix it up. So I'm going to integrate term by term. Integral of w squared, I add 1 and I get w cubed and I get a 1/3 here. This constant multiple of 3 gets carried along, so it's 3 times. And when I try to use the power rule on this one, if you're just sort of marching along mechanically and not thinking, you might try that. You might say, oh, okay, I add 1 to this exponent. Negative 1 plus 1 is 0. That looks good. And then I do the reciprocal of 0 in front of it. But, uh-oh, I end up with 1 over 0. And that is something that is undefined. And sometimes it's so funny because sometimes I'll see students try so hard to make this work by going ahead and saying, oh, 1 over 0, that's 0, or 1 over 0 is 1. They'll try anything they can because they're stumped. They're sitting there thinking, wait, I used the power rule and it didn't work. Let me put my plus c on here because I can't stand to not put the plus c on. But that doesn't work. And remember that negative 1 was, unfortunately, the one power of our variable that was excluded in the power rule. It does not work. So this is not the way to integrate 3w to the negative 1. So you probably remembered how to do it. So I'm going to just sort of scratch this whole line out. Let me scratch it out in a different color. So I'll just cross that out. That wasn't good. So let me go back up here and try to do this correctly. So I'm going to write it out nicely. It's the integral of w squared dw, and I'm going to break it up. The 3 here is definitely constant multiple, so that can be pulled outside of the integral sign, no problem there. But when you get a w to the negative 1, it's better to write it this way, as 1 over w dw. In fact, I could have just skipped this line altogether, and when I reduced this, I could have written it as 3 over w instead of 3w to the negative first. So, okay, this one we already did. That one was fine, 1/3 w cubed. And here I pull along the 3, and now you have to remember what is the integral of 1 over w dw. Well, remember that was one of our special formulas from, I believe, a couple of pages back. I don't know if I have that on my desk here. I don't think I do. That was one of our special formulas. You have to think back and think, oh, well, what function do I have to start with so that when I take its derivative, I end up with 1 over w, and you would have to start with the natural log of the absolute value of w. So that was one of our special formulas as well. So here's my answer. And unfortunately, the power rule didn't work for that one. And sometimes it's hard to remember that as you're sort of mechanically going through it. But as soon as you see that 1 over 0, you know that's your little warning red flag that, no, that doesn't work. And you have to rethink it and think, wait, I could write that as 1 over w instead of w to the negative 1. And then I can recognize fairly easily, yeah, when I take the derivative of ln of absolute value of w, I get 1 over w. Okay, let's look at 2 last examples, and these are kind of a little bit tougher ones. So again, I want you to think about them because I always like to give my students practice thinking, even if you don't get the answer, the thinking process, the struggling with it is the really important part, especially if you then restart the video and we go through it together and you see how to do it. But it's always so much better for you to try to think it out on your own. So think about these two examples, get as far as you can with them, and then we will go through them together. Let me just remind you again that this particular example has a product in it. So think about that. And this particular example has a quotient in it. These are integral problems, not derivative problems. So give those a try. Okay, well, let's go ahead and look at the top one. As I mentioned, I have a product of secant x and this other function, tangent x plus secant x. There's no product rule for integrating. And so somehow I have to rewrite this before I integrate. And really the only thing I can do is to distribute this secant out to get a sum of two terms instead of a product of two factors. So let me do that, and I would have the integral of secant x tangent x plus secant x times secant x would be secant squared x. And that is at least better in the sense that now I have the integral of a sum instead of the integral of a product of two things. And I'm allowed to integrate term by term. So this will be the integral of the first term, secant x tangent x dx, plus the integral of the second term, secant squared x dx. And hopefully those are starting to look familiar to you because you're getting used to thinking backwards. Secant x tangent x, we want to think, what function do I need here so that if I differentiated it, I would end up with secant x tangent x. And the function whose derivative is secant x tangent x is secant x. And for this one, I'm thinking backwards, what do I have to start with? That when I differentiate it, I would get secant squared x, and the function I need to begin with is tangent x. And then I just add on a single integration constant. And again, you can check it in your head. Derivative of secant x, yeah, that's secant x tangent x. Derivative of tangent x, yeah, that's secant squared x. And so I know, at least back to this step, that my answer here looks correct. So hopefully you were able to figure out how to rewrite that in a way that you could then find the set of all antiderivatives. Okay, this last one's especially tricky. There are a couple ways actually of doing this. So let's talk about both ways because you might have done it either way. One way would be to do it in a similar manner to what we did in the last example. We do have a single term in the bottom. It's not something plus something in the bottom. So you could do it the way that we did that example at the end of the last page. Remember this one? I said there's a single term, so we split it into two different fractions. And you could do that here. There's a slightly faster way that we'll talk about, but that might be a completely natural thing to try since we had just used that technique on that last example on the previous page. In other words, write this as secant squared theta over cosine squared theta plus cosine squared theta over cosine squared theta. So you might have tried that, and what do I get though? I would end up with secant sine squared theta over cosine squared theta is the same as tangent squared theta plus cosine squared theta over itself is going to be equal to 1. And this is actually a little bit tricky. You would have to remember your trig identities, and you'd have to remember all of your trig identities, but you might remember that tangent squared theta, there's not a lot I can do with that. I can't use the power rule on it because it isn't just theta to the second, it's a function of theta to the second. It's tangent of theta raised to the second. And unfortunately at this point we haven't really talked about an integral technique that works when you have a composition of two functions, an inner function and an outer function. And none of our formulas for the derivatives of the trig functions, none of those formulas involved a tangent squared theta. So all we had were these formulas for cosine secant squared but not tangent squared, secant tangent, and cosecant squared but not tangent squared. So none of those will really help us. But we could actually do this if you remember that there is a trig identity that says the following. Tangent squared theta plus 1 is the same thing as secant squared theta. So I'm going to put down here, that's actually a trig identity from back in trig, or you may have seen it in pre-calculus, that those two things are the same for any angle theta. So these two things are equal. And at that point, you could go ahead and say, oh yeah, I do know how to integrate secant squared theta. That was one of our formulas. And the function that I need down here, whose derivative is secant squared, would be tangent theta. And then just add on your integration constant. That would probably be sort of a natural way to go through the problem, but there is a slightly faster way, and a way that involves a much simpler trig identity that usually everybody remembers, because sometimes people don't remember some of these more obscure trig identities. And if I went back to the original problem right here, can you see a trig identity that would greatly simplify this before I even try to integrate? Notice in the numerator I have a sine squared theta plus a cosine squared theta. And there's another trig identity that almost everybody remembers, since it's one of the most basic trig identities. And what does it say sine squared theta plus cosine squared theta is equal to? Remember, sine squared theta plus cosine squared theta for any particular angle theta is just equal to 1. So you may have recognized that, and if you did, bravo, that is probably the easiest way to do this problem. So this whole numerator for any particular angle theta is just equal to 1. And then I have divided by cosine squared theta, d theta. I'm still a little bit stuck because I have no way initially to integrate 1 over cosine squared theta either. But 1 over cosine squared theta, how could that be rewritten? That could be rewritten as secant squared theta. So now all I have left after rewriting this a couple of times is the integral of secant squared theta to do, and that's exactly the one we did down here. We got to exactly the same function to integrate, and so I end up with tangent theta plus c. And that would be a little bit quicker way to do the problem, but you notice that we ended up with exactly the same answer. So if you did it this way, it's fine, but you can see this is a little bit faster. And I just want to remind you that whenever you're working with integrals that involve trig functions, you want to kind of keep in the back of your mind all of those little trig identities that you learned back in trig or in pre-calculus, because a lot of times you can simplify your problem greatly that way. And all of the trig identities can hide something that makes something look very complicated that actually could be rewritten in a much simpler way, the way that we rewrote this sine squared theta plus cosine squared theta as simply a 1 makes it much simpler. Well, that's about all we're going to talk about in this video on indefinite integrals and antiderivatives. And now what we're going to do is to go on to a new section in which we talk about something that probably will seem very unrelated to this idea of antiderivatives and indefinite integrals, and that is the idea of areas. In particular, we'll be looking at areas underneath a function y equal f of x, underneath the graph of a function. It will seem totally unrelated, and we'll be talking about that throughout the next video, and later on when we get to section 5.3, I think I wrote it down as 5.3/5.2, we will make a connection between all this stuff that involves antiderivatives and all the stuff we're about to talk about next, which involves areas. So keep that in mind, that there will be a kind of a magical connection between what appears at first to be